Hi, this is Adam from the classroom. In this video, we'll discuss prime numbers. Prime numbers, as we've discussed previously, are natural numbers which can only be divided by two numbers, itself and 1. The first 5 prime numbers are 2, 3, 5, 7, and 11. 1 is commonly misinterpreted as a prime number, but since it can only be divided by 1 and not a secondary number, it isn't a prime. The way we can identify primes is by using the Sieve of Eratosthenes. Let's look at how this is done. Eratosthenes posits, or posited rather, that as we go through the numbers, we can divide them by primes that came before it to see if they are also primes. It's easier to see this in a visual. As we can see here in the 100 square, we know that 2 is the first prime number, so we can eliminate any other numbers that can be divided by 2. The next prime number is 3. Which allows us to eliminate any numbers that are divisible by 3. We can do the same with 5 and finally 7. Now all the remaining digits are prime numbers. Now that's big talk, so we need to know how to do it for ourselves. We first need to know how to find the multiples of 2, 3, 5, and 7. So let's figure that out with an example. Let's look at the numbers between 40 and 60 for our example. We know that all even numbers are in the table of 2, so we can eliminate any even numbers. We also know that any numbers ending with 5 or 0 are in the table of 5, so we can eliminate those as well. Now for 3. We can check if a number is a multiple of 3 by adding the digits up. If the final answer we get is in the table of 3, then the original number is also in the table of 3. We can do this for our remaining digits. For 41, we have 4 plus 1, which gives us 5. That's not in the table of 3, so that means we can leave it for now. The same happens with 43, 47, and 49. When looking at 51, we add 5 and 1 together to get 6. We know that 6 is in the table of 3, which means that 51 is also in the table of 3. That allows us to eliminate it from our list. 53 adds up to 8, which means it's safe, and 57 adds up to 12, so we can eliminate it as well. 59 is also safe as it adds up to 14. Now we're left with 41, 43, 47, 49, 53, and 59. Now we can finally start looking for the numbers that are in the table of 7. There is a way to check if a number is in the table of 7, which involves removing the ones place, doubling it, and then subtracting it from the remaining digits, which is a little bit convoluted, but I'll explain it anyway. For this example, we'll take 483. If we remove the 3 and double it, we get 6. Now we subtract 6 from the 48 that was left behind, which gives us 42. 42 is in the table of 7, so 483 is also in the table of 7. In all honesty, this is a pretty complex and awkward process, so I'd recommend just attempting to check the table of 7 by just dividing, or noting down the multiples and using it as a reference. Now you might ask, Adam, why bother mentioning it if you think it's a bad idea? To that I say, I actually don't have an answer, but I thought it would be useful to reference. So if it works for you, fantastic. If it doesn't, just fall back on the times tables. In all honesty, numbers that are higher up in the table of 7 aren't common in exam questions. So as long as you know the table of 7 through till 12, you'll be fine in almost all cases. Now, going back to the digits we have left, the only number that is in the table of 7 is 49. We can see this using the method mentioned previously, by removing the 9 and doubling it, making it 18, and subtracting it from the 4. This gives us a negative 14. We know that 14 is in the table of 7, so that means that 49 is also in the table of 7. Or if you already knew what 7 times 7 was, you already knew that. So when we remove it, we get our final list of prime numbers. Now let's do a practice set. Find the primes in the following numbers. Take a moment and continue when you're ready. Okay, so first we eliminate all of the even numbers and all of the numbers that end with 5 or 8. Now we're left with 4 numbers. Now we can eliminate the ones that are multiples of 3. Looking at this breakdown, there are none. Finally, we check for any that are in the table of 7. We know that 77 is in the table of 7 by 7 times 11. We can also check using the method mentioned previously, removing the first 7, multiplying it by 2, giving us 14, and subtracting 14 from the 7. We are left with negative 7, which tells us that 77 is in the table of 7. Lots of 7s. Thus, we get a final list of 71, 73, and 79 as our prime numbers. For notes, we have the divisibility checks and the recommended order to do them in. Always start with 2 and then 5 because they're the easiest. After that, go for 3 because you're more likely to get a number in the table of 3, and then finally 7. After that, you should have the list of primes. Test it out on a couple of sets, so between 20 and 30 or 70 and 80, you get the idea. Then you can cross-reference it with the 100 square to check, or if you're using bigger groups, maybe up in the hundreds, 120, 130, that kind of thing, you can look it up online to see what the list of primes are and see if you manage to pick them out correctly. You can find a printer-friendly version of these notes at the link in the description. Thank you for watching, and I hope this video was of help to you. Take care, and I'll see you next time in the classroom.